And you can see that in this figure here, where we're looking at, we have the bulk solution out here. These are our molecules, so we'll look at these as copper ions from that first. We have a stagnant layer surrounding our particle. So those copper ions have to diffuse through that stagnant layer. They then have to diffuse into the micropore. So you can see that here. And what this attempts to show is that at equilibrium, we have these, in this case, we'll think of these as copper ions. The copper ions sorbed to the solid surface, and the open circles are the copper ions that are still in solution. So we can think about this now as an example where in this case we have 100 milligrams per liter of total organic carbon. We add 2 liters of that solution into 4 beakers. So this is typically how we would do what we refer to as an isotherm experiment. It's iso, same therm temperature. So we want to do these at the same temperature. So we've got these 2 liters of solution containing 100 milligrams per liter. So this is our initial concentration. In the first one, we'll add 3 grams of activated carbon, 5 grams in the second, 7 grams in the third, and 0, our control, in the fourth. We're going to mix and we'll allow the system to come to equilibrium. When it's come to equilibrium, and typically what we do is we do a kinetic experiment first to determine how long it takes to reach equilibrium. We then determine the concentration at equilibrium. So these are the equilibrium concentrations. And we can determine then the mass of TOC that is adsorbed per mass of carbon. So for example, if we start at this 100 milligrams per liter and we have 2 liters, so that means the mass initially is 200 milligrams. So the mass adsorbed per mass of adsorbent is equal to 200 minus 50 over, actually, the C equilibrium is 50 milligrams per liter times 2 liters. So that's 100 milligrams. So that is 100 milligrams divided by 3 grams, and that is 33.3 milligrams of TOC absorbed per gram of granular activated carbon. So that gives us the mass adsorbed. And we could do the same sets of calculations for both the 5 and the 7 gram solutions. And what we would end up with is a graph that actually would look something like this if we plot what is referred to as X over M, the mass of sorbate divided by the grams of sorbent divided by the equilibrium concentration. If we plot this data, we would end up with a graph like that. We typically model these systems by what are referred to as isotherm models. There are a number of isotherm models. I will only talk about a few of these. There are probably 10 or so different types of isotherm models that you can use. The Freundlich isotherm is entirely empirical, and what it states is that the X over M value is a function of the equilibrium concentration to the 1 over N power. So this is entirely empirical. And we can linearize that by taking either the natural log or the log base 10 of x over m. That equals 1 divided by n times the natural log of the equilibrium concentration plus ln of k. Okay, so this is our y-intercept, and this is our, so we're plotting ln x over m versus ln of the equilibrium concentration. The Langmuir isotherm, which we'll talk a little bit more about, is actually thermodynamically derived. So it has some basis in thermodynamics. Here we linearize it by plotting 1 over x over m versus 1 over c sub b. That's how we linearize the Langmuir. And then we have what's referred to as linear isotherms. These are for much lower concentrations, and these are typically used with soil or sediment systems. And here, for instance, what you're looking at is the concentration of the chemical in the organic component of the soil. So you can see it's actually micrograms sorbed instead of milligrams, it's micrograms, 1,000-fold less per kilogram of soil organic matter. So you're really looking at that soil organic fraction. We also talk about soil water partition coefficients, and here now you're looking at the actual concentration in the soil itself, so the bulk soil, and that is related to this KOC value as a function of the fraction of organic matter. We also talk about octanol water partition coefficients, and here you're looking at what we refer to as KOWs, and these are the concentration of your contaminant in octanol divided by the concentration in water. And we use that to try and predict the concentration of a chemical in cellular material, especially in fatty tissue, because that's often where organics accumulate in an organism. And then sometimes we will also talk about bioconcentration factors. And here we're looking at the accumulation of these organics in an organism. And this is the concentration in the organism divided by the concentration in water. So for instance, we're looking at the concentration of PFAS chemicals in fish. So we're looking at how much does that organism accumulate these chemicals. So as I mentioned, the Langmuir isotherm is thermodynamically derived. And this A term here is related to the mass required to achieve monolayer coverage. If you think about these sorbents that we talked about, much of it is actually going to be in the porous structure. What you're thinking about is how much chemical can actually sorb, and you only have one layer. You don't have the adsorption, for instance, or the accumulation of multiple layers of chemical. This K is actually thermodynamically derived. So if we think of this as a vacant site on the sorbent that can react, that reacts with your chemical to produce a surface complex. This K is the equilibrium between the surface complex, the vacant site, and the chemical in solution. So it's truly thermodynamically derived. So we assume here that chemicals can only attach on a monolayer coverage. we have a limited availability of surface sites, that adsorption is reversible, that we reach equilibrium, and that, for instance, one site, so the absorption of, let's say, copper here, doesn't affect absorption at an adjacent. So that's the basis for the Langmuir isotherm. And you can see here we've got some data plotted where we're plotting this X over M ratio versus the equilibrium concentration. And as I mentioned, we linearize this by taking the inverse of the concentration and the inverse of X over M. We plot that. The y-intercept is 1 over A, and the slope is 1 over A times K. So from that, we can determine both of these parameters. So we can see that, well, here we have the Freundlich isotherm. So this is, as I mentioned, totally empirical. We're plotting X over M versus the equilibrium concentration. And we describe the relationship with a power function. We linearize this by taking either the natural log or the log base 10. And log of K is our y-intercept, and 1 over N is the slope. And what you can see here, for instance, at log equilibrium concentrations greater than about 0, that this carbon is the best. If your equilibrium concentrations are less, then this carbon is the best. And in no case, except maybe if we went to very, very high concentrations, would this carbon be the optimal. So we can use this to try and do empirical studies, determine these parameters, model the adsorption, and then what we will do is we'll use this information in the design of these